Hello all, welcome to the part A of lecture 8. In this lecture, we are going to discuss how we can use regression model, simple regression model for time series data. Time series data is very common in data science, and whenever we see a data that comes with timestamp, typically that is called time series data. So far, we have seen data like MTEL-NOC data or Diamond's dataset. These datasets are not timestamp data. So these datasets typically will be collected at a particular given point of time, and these datasets are typically known as cross-section data. In time series data, what happens is each observations when it is collected will be their timestamp, like time, minutes, hours, day, which date of the year, all those things, all those information will be collected and as one column or several columns. But overall, the time, these kind of data are called timestamp data or time series data. So regression model is one of the most commonly used statistical tools for forecasting time series data. Okay, and we will see how can we use the regression model to forecast time series data. So two kinds of forecasting depending on what is your objective. So one objective is long-term forecasting. You want to forecast in a long term. If you want to forecast long term, then modeling trend and seasonality as a function of time is very important, and a lot of effort we have to put in modeling trend and seasonality of the time series data. Another objective is short-term forecasting. So in short-term forecasting, we typically interested in forecasting for next time period or next 2 time period. That's it. Maybe next 3 time periods. That's it. You will not even go up to 4 time period or 5 time points. But if you want to do a long time, like quarterly forecasting or for a forecast for 1 year or 2 years ahead of time, then that kind of forecasting will be a long-term forecasting. But if your data is a monthly data and you just want to predict the next month demand, or if it is a weekly data and you just want to predict next week's demand, then it will be a typical called a short-term forecasting. Just 1 time ahead or 2 time ahead forecasting will be considered as a short-term forecasting. In that kind of forecasting, we are not necessarily interested in the trend and seasonality that much. We are more interested in the local correlation and local feature of the data. So in this case, typically we detrained the data, and auto-regression models are very good in using this kind of forecasting model. So we will discuss that in both kind of modeling, both kind of objective, long-term forecasting and short-term forecasting, regression model can be used. So in order to understand long-term forecasting with trend, we will consider this AirPassengers dataset. This is a small dataset but very good for understanding the concepts. As I discussed in my live session also, that small datasets are good for understanding the small basic concepts, and in the hands-on we will use long and more complicated big data. So in this AirPassengers dataset, we have monthly number of people who traveled through in air in US between I think 1949 to 1962, around this time period. And what we are going to do, we are going to take up to 1957, this period which is marked with purple as training data. Okay, we are going to use it as a training data, and this period we are going to use as test data. Okay, so we will build our model based on this training data, and then we will do the forecast here. We will do our forecast here and see how good our forecast will be, and check how good the forecast is. Okay, so this will be our main objective. So first thing is to model the trend of the AirPassengers data. First thing we will try maybe a linear or quadratic function as a function of time. So suppose YT is the number of monthly totals of international airline passengers. So that is the value, and T runs from 1949 to 1960. So it's from 1949 to 1960, every month how many international airline passengers were traveled, that is being reported. So if we think that there is a linear trend, what we will do, we will just fit a simple YT is equal to beta naught plus beta 1 T plus epsilon T. Okay, and if you see the data, so you see 1949, this is Jan and this is Feb. Okay, Feb of the 1949. So what is happening is it is 2 out of 12 basically. So that gives you 0.83. And this is March. March is kind of 3 out of 12. That has given you 1949.167. So that's how the months are being converted into a numeric value. Okay, so this is my T or Tm, simple T or Tm, and this is the Y of T. Essentially, these are the values. These are these many people, or these many in 100,000s, 112,000, 118,000, 132,000. In that month, people have traveled through air. So we can just simply put them into a simple linear regression framework, and our design matrix will be 1, 1, 1 on the first column. It will be intercept, second column will be T, and beta will be beta naught and beta 1. This is Y1 to Yn. And now if you fit this model, this will be the final estimates of the model. This is beta naught and this is beta 1. These are the standard error, these are the T value, and the P value is so small that it is pretty much rounded up to 0. So adjusted R square turns out to be 816. So almost 81% of the entire variability of the data can be explained through the trend. So 81% of the variability of the data can be explained through the trend. So 81% of the variability of YT can be explained through linear trend. Okay, and if you fit this simple linear trend, this is the simple linear trend and this is the forecast. So clearly it can pick up the trend, model the trend correctly, but if you plot the residuals, clearly residuals pick up the seasonality. Okay, now we have to model the seasonality. So how we model seasonality? So we can model seasonality RT residual as a function of alpha naught plus alpha 1 sine omega t plus gamma 1 cos omega t. Now what is omega? Omega we are going to take 2 pi by 12. Since we have a year, so we can take a 2 pi by 12, and if we fit this model, simple model with Fourier transform, you can see that simple one Fourier transform can be modeled the residual to a greater extent, but you can see that these models are not, these are the places where it is not very well captured. Now what about after we stopped after first Fourier transform, what about we are taking the second Fourier transform? So we can just after that we can just alpha 2 sine 2 omega 2 cos 2 omega 2, and you can clearly see this red line, purple line is the real the residual, true residual or residual observed, and these red line is the estimated from the model. So clearly when you put the second Fourier, it tries to capture this curve, it tries to capture this particular change, this seasonality, this summer. It is, I think this is the summer kind of, before summer kind of peak curve that is getting picked up. So now if we join the trend and seasonality, we define our model alpha plus beta t trend, alpha plus beta t as trend. This is the trend part, and this is the seasonality part. The seasonality you can put as many Fourier transform as you want, and plus epsilon t of course, and omega is 2 pi by 12 because we want, it's a monthly data that we have, therefore the frequency is 12. If we had quarterly data, what would be the frequency? Just figure out, ask yourself, take a break, maybe pause your video for 5 minutes, ask yourself if you have quarterly data, what would be your omega or frequency? So 2 pi by what, which value you should use. All right, next. So if you use this, if you fit this model and if you forecast this green part, this green thing, then forecast kind of gives, and then on the top of that, if you just, blue one is the actual data, it picks up the seasonality, but it clearly misses all the peaks in the summer. It clearly misses all the peaks of the summer. It misses the peaks of the summer. Now, in this situation, we thought like, a transformation might help, because if you look at carefully, it looks like these peaks are increasing at an exponential rate. So no harm, try to model it as exponential transformation or after a log transformation. So I kept the right side of the model exactly same, but on the left side, instead of modeling yt, I took log of yt. And when I did that, looks like during the fitting part is doing pretty decent, and in the forecast also looks like it has done quite decent work. In the out of the sample forecast also it has done quite work, and then when we put the real values, it is almost matching exactly. So when you, and here it is, we are considering these are all long-term forecasting for 1, 2, 3, 4, almost 4 years we are forecasting the trend and the seasonality, and it is doing pretty decent job. Now next we will move on to modeling short-term forecasting. Here our objective is forecast only 1 month ahead or maybe 2 months ahead, not more than that. In this kind of situation, our idea of autoregressive model is very useful. Autoregressive model is useful. It's very useful. So how the data structure works? So what you have to do, you have to just create a bunch of lag variables. So we will start with one. So this is my data. Actually, this is my data. T1, T2, Tn, Y1, Y2, Yn. And then I just create a lag of Y. What is lag of Y? So in the time point 2, Y2 is being observed. And what is the one variable, lag variable? So that is Y1. So that is Y1. Similarly, if you have a T3, Y3, what will be the lag variable? Y2. So at the end, Tn, Yn, the lag variable is Yn minus 1. So you create a lag variable. In the data set also we created a lag variable. So just by placing in this way, we created a lag variable, and our plan is, and what you can do is essentially take the differences of the lag variable. So define the first difference of the yt in log scale as log yt minus log of yt minus 1, because log yt is we found that in the long run forecasting was very good, so we just take the differences of the so dy is essentially this guy. You take the log y and take the consecutive differences, and then you can take the lag of even this first difference order variable as well. So this is how you create the lag variable. Now you see, if you just plot on the y-axis yt minus 1 and the yt, you can clearly see that there is a increasing trend. But what is happening, and these purples are all training data points and blues are all test data points. These purples are training points, and these blues are test points. Okay. And if you fit the autoregressive model of yt as a function of yt minus 1, and you can do after fitting the model, I did a Bruch-Pagan test on the residual, and the p-value is very small. I am not surprised p-value is very small. That means there is a big bunch of heteroscedasticity, because you see at the beginning there is a kind of tight. In the training data was kind of tight, but the test data was kind of spread out. So the residuals are not homogeneous. Residuals are heterogeneous. So I am not surprised that Bruch-Pagan test will reject the homoscedasticity and it will go for heteroscedasticity. So I have taken the log y t minus 1 and log yt and plot them. And now it looks like they are somewhat homogeneous behavior. There is a somewhat homogeneous behavior, which is probably correct. Now, if you fit this log yt beta naught plus beta 1 log yt minus 1, you see that Bruch-Pagan test p-value is very high. So that means it cannot reject the null hypothesis that it is homoscedastic, residuals are homoscedastic. So the residuals are homoscedastic, that assumption is correct, and this is indeed a good starting point for lag 1 autoregressive model. So what is the idea of autoregressive model? If you basically now fit this, plot this delta of log y over the time period horizon of 1950 to 1960, then what you will see that these differences is essentially mean stationary. It essentially means stationary. It's a mean stationary, where it means stationary at 0. Okay, so this is the first thing, but still we can see there is bunch of seasonality we can see. We will talk about it, how can you do that. And then here what I have done, I have plotted the delta log yt minus 1 and delta log yt. And what we are finding is there is a circular hole in the data. Okay, and this is effectively shows that how the seasonality is affecting there is still good decent seasonality, and this is typically called in the circular topology, and this falls into the category of topological data analysis. So I'm not going to discuss about this, but topological data analysis is a new top area, and it's a very exciting area. That what is the topology of the data? Understand, is there a hole in the data? And what we are seeing that there is indeed a hole in the data. So here I have plotted the fitted values against the residuals. What we are seeing that there is not much is going on, which is a good news for us. And then when we took the data, plotted it, and what we found that autoregressive model is almost one order. Autoregressive model was almost mimicking the data, because it's just forecasting only in the next step. So, and in the out of the sample also it is almost mimicking the data. So it's pretty good in terms of forecasting the model. So other time series models such as ARIMA model, GARCH model, state space dynamic model, spectral analysis model, most of these models are non-linear in parameter. So simple trend and seasonality model for long-term forecasting and autoregressive model for seasonality for short-term forecasting is regular regression model with which is linear in parameter. But these models, these are very popular time series model. These are not linear in parameter, they are non-linear in parameter. So these models are right now beyond the periphery of this course. We have to, I will offer a full course on time series modeling, of course I will discuss all this model in that course. Hence we cannot model them easily using regression model setup. Okay, so I'll stop here. Next we will do a hands-on, and then we will discuss another nice application of regression model known as grandeur causality model. So for now I will stop here. Thank you. See you in the next video.